Beneath the busy intersection at Times Square, water tunnels run as deep as 1,110 feet below sea level, carrying 981 million gallons of water daily, while 105 miles of steam pipes lie just 10 to 30 feet below street level. Millions walk these streets oblivious to the massive subterranean network beneath their feet that moves electricity, water, internet, wastewater, steam, and natural gas. Yet no single map of all these interconnecting systems exists. Water from treatment plants flows into massive underground aqueducts, then branches into thousands of smaller distribution lines. Manhattan's water mains range from 6 to 16 inches in diameter, with a minimum of 8 inches where fire hydrants connect. These arteries maintain pressure between 35 to 60 pounds per square inch at street level, enough force to push water to the top of six-story buildings without pumps. Individual service lines taper to 1 inch in diameter, delivering 9 gallons per minute, while 1¼ inch lines deliver 16 gallons per minute, 77% more capacity. Every connection requires a minimum of 55 pounds per square inch at street level to ensure adequate flow reaches the highest fixtures. The system calculates exact pipe sizes based on building demand, turning what appears simple, turning a tap, into a precisely engineered network of pressures, diameters, and flow rates that must work simultaneously across an entire city. Here's what blows my mind. When you turn on your kitchen faucet on the 20th floor of a Manhattan apartment, you're tapping into a pressure system that was calculated down to the exact pound per square inch needed to overcome gravity and deliver water to your exact location. Every single tap in the city is part of one massive hydraulic equation that must balance perfectly, 24 hours a day. 20 feet above those water mains, underground fiber optic cables carry digital signals through hair-thin glass strands that move data at light speed. These cables snake through protective conduits buried 12 to 24 inches deep in residential areas, or up to 36 inches in high-traffic commercial zones, close enough to surface that a misplaced shovel can sever internet service to thousands of homes. Each fiber strand transmits signals using pulses of light that can travel 40 to 100 kilometers without amplification. Recent expansion projects include underground fiber installations across multiple counties, while various projects have installed miles of cable through underground conduit systems. The network creates redundant pathways. If one cable fails, traffic automatically reroutes through alternate fiber paths, ensuring uninterrupted service while repair crews locate the break. Think about this. Right now, as you watch this video, light pulses are racing through glass, thinner than human hair, buried just 2 feet below the sidewalk outside your window. Those light pulses are carrying this very video to your screen at nearly 200 million meters per second. And here's the crazy part. One accidental shovel strike by a construction worker can instantly disconnect thousands of people from the entire internet. The digital backbone of our civilization hangs by threads of glass buried barely deeper than a flower garden. Think about those hair-thin glass strands carrying light signals at 40-kilometer distances without amplification. Have you ever wondered what happens when someone accidentally cuts one with a shovel? Comment your answer below. Now let's see what other systems share this same vulnerable underground space. Subway tunnels carved through rock and soil at depths of 50 to 70 feet underground, threading massive tubes between every other underground system without disrupting the city above. The real engineering challenge isn't depth, it's precision coordination in congested urban space. Imagine being the engineer who has to tunnel a subway line through the underground equivalent of a three-dimensional jigsaw puzzle. You're boring through solid rock while navigating around water mains that can't lose pressure, gas lines that can't leak, and fiber cables that can't go dark, all while keeping the buildings above from cracking or settling. One miscalculation doesn't just delay your project, it could flood a tunnel, black out a neighborhood, or worse. For deeper tunnels and heavily congested urban centers, the tunnel boring machine method excavates horizontally while simultaneously removing material and installing permanent tunnel lining. These machines must calculate exact pressure to prevent tunnel face collapse while avoiding settlement that could crack buildings overhead. In soft soil, engineers deploy an earth pressure balance machine, which uses excavated material itself to maintain pressure against the tunnel face. The machine conditions soil with foams and polymers to make it more plastic and impermeable, allowing the material to serve as a supportive plug that precisely balances external earth and water pressure. This controlled balancing act prevents soil from flowing into the tunnel and minimizes ground subsidence that could damage surface infrastructure. Once complete, these tunnels require massive ventilation systems to keep millions of passengers breathing safely. An efficient ventilation system can expel smoke and harmful gases from the tunnel in 5 minutes during a fire, buying valuable time for passenger evacuation. Here's something that will change how you think about your morning commute. Every breath you take on the subway is carefully engineered air. Those massive fans you hear rumbling, they're not just moving air, they're calculating the exact volume needed to keep you alive if disaster strikes. In a fire emergency, these systems can completely replace all the air in a tunnel faster than you can hold your breath 5 times. Electrical conduits and gas mains must thread through the same underground maze without triggering catastrophic failures. All electrical infrastructure requires a minimum horizontal separation of 36 inches from gas and water lines, while vertical separation requires at least 12 inches when crossing other utilities, with sleeves or concrete encasement when electrical lines cross gas mains or other critical services. Gas lines are staked every 10 feet to maintain separation, creating a three-dimensional coordination puzzle where every pipe and conduit navigates around existing infrastructure. When primary electrical conduits carrying over 600 volts share trenches with secondary lines under 600 volts, both must meet primary depth requirements with minimum 2-inch separation. Primary conduits positioned on bottom at required depth, secondary conduits on top maintaining 2-inch minimum separation. Picture this nightmare scenario. You're an engineer laying new gas lines in Manhattan. Every 10 feet, you have to mark exactly where that pipe will go. Because just 36 inches away in any direction, there's probably a high voltage electrical line carrying enough power to light up a city block. Get the measurements wrong by even a few inches, and you've created a potential bomb buried under one of the world's busiest cities. Safety systems preventing disasters operate through precise engineering calculations. Protection devices shut off power in milliseconds when detecting ground faults, while gas detection systems monitor for leaks continuously. When electrical sparks meet escaping gas in confined underground spaces, the result is explosive. These detection systems and mandatory separation distances exist because the cost of failure isn't a repair bill, it's catastrophe. The coordination challenge is staggering, thousands of systems occupying the same three-dimensional space without interfering. New York City has launched a major 3D mapping platform to digitize underground utilities and soil conditions citywide. A specialized filter system will integrate inputs into one usable interface, finally solving the puzzle that has plagued urban infrastructure for centuries: how to coordinate thousands of underground systems without catastrophic conflicts. The project brings together city agencies, utilities, and regulatory commissions, with major universities digitizing thousands of boring records to model the city's geology. Before this initiative, mapping software choices ran such a wide range that linking two sources into a compatible visual could take weeks. Lack of coordination led to costly excavation strikes, construction delays, and dangerous uncertainty in emergencies. Here's the revelation that should terrify and amaze you. Until now, no one, not the mayor, not the utility companies, not even the engineers, has ever seen a complete picture of what lies beneath our cities. Every time someone digs, they're essentially playing underground Russian roulette, hoping they don't hit something that could kill them or shut down half the city. We've built the most complex urban infrastructure in human history, and we've been operating it essentially blind. When this digital twin launches, engineers will finally see what has always been invisible: the complete three-dimensional relationship between every pipe, cable, and tunnel beneath the streets. No more blind excavation where that critical 16-inch water main crosses beneath fiber optic lifelines. No more disaster crews clawing desperately through earth in the dark. The hidden metropolis beneath your feet will finally surrender its closely guarded secrets. This invisible complexity beneath our feet represents more than just an engineering marvel. It's a glimpse into the future of how we build cities. As urban populations explode worldwide and climate change demands smarter infrastructure, the lessons learned from mapping these hidden networks will shape how the next generation of cities rises from the ground up. The age of building blindly beneath our streets is ending. What emerges from this underground revolution will determine whether our cities can handle the challenges of tomorrow, or whether they'll buckle under the weight of their own invisible complexity. Hit subscribe for more hidden engineering and check out that next video. It reveals how skyscrapers actually stay standing.